This is Quick Clip 1.09 Mechanical Energy Conservation, and in our last video we ended up with this screen here discussing how a ball falling from a great height will have different potential and kinetic energies as it falls. So looking at its position at the top, we found that its potential energy came to 784 joules, and because it was not moving yet, its kinetic energy was 0 joules, giving us a total energy of 784. Now when the ball drops, we calculated the PE and KE when it was halfway, and we found that the potential energy was 392 and the kinetic energy was also 392, and so it was a 50-50 split between potential and kinetic energy, giving us again a total of 784 joules. And then finally, when the ball was about to reach the ground, its potential energy was 0 and the kinetic energy was 784, and again giving us a total of 784 joules. So the idea being is that when the ball was placed at the very top of the building, it was provided a certain amount of energy, right, in the form of potential energy. That total energy of 784 never changed as it falls to the ground. And that leads us to the idea of mechanical energy and its conservation. So the total mechanical energy is defined as the potential energy plus the kinetic energy. And we saw that with the ball falling, where no matter where the ball was in its flight, I guess we can call it, from the top of the building down to the ground, its total energy was where it started with, 784 joules. Now, in a lot of other situations, mechanical energy is not conserved, and it has to do with the idea of friction. Just like if you slit something across your table, it's not going to just keep going and going and going. Friction gets in the way of that system. So a lot of times we'll see that mechanical energy will equal the potential energy plus kinetic energy, but some of that is lost to friction in the system. All right, next we're going to go to a simulation that will further illustrate the entire idea of mechanical energy being equal to potential plus kinetic energy. Okay, in this simulation we're going to take a look at the skateboarder that's going to ride this half pipe. On the left we have a bar graph, and that will show the amount of potential energy, kinetic energy, and the total energy that the skateboarder has. So what I'll do, I'm going to bring the skateboarder up to the top of the half pipe, and you can see I've loaded him up with potential energy. And right now he's not moving, so the potential energy is equal to the total energy. Now if I brought him down lower, all right, I'm controlling him, he's not moving yet, I haven't released him yet. If I bring him down, the total energy and the potential energy will decrease. All right, so let's bring him all the way up, and I'll let him go. And what you'll see in the bar graph, you'll see how the kinetic energy in green and the potential energy in blue will change as the skateboarder travels. As potential energy increases, kinetic energy decreases, and vice versa. So I'm going to release him. It'll be in slow motion, and you can see that as potential energy increases, kinetic decreases. As kinetic increases, potential decreases. All right, so he's full of potential energy there, and at the bottom, all right, at the bottom, he's full of kinetic energy because it's as fast as he's going to go. And he's at the very bottom, so there is no potential energy. When he continues to go up the ramp, then he's going to lose speed and lose kinetic energy, but he's going up, so he's going to gain potential energy because his position is changing and he's rising higher above the ground. So he's at the top right here, and so his potential energy is the greatest, and he's about to reverse course. He's going 0 meters per second, so his kinetic energy is 0. And you can see that change. And so the conservation of mechanical energy says that when you add the kinetic and the potential, you're going to get a total mechanical energy. So anywhere I stop the skateboarder, if we add the potential bar onto the kinetic bar, you are going to add, or you're going to get a sum that's equal to the total energy. All right, so if I let them go again, and then we have, a tall green one and a short blue bar. If we put those two together, those two bars will equal the height of the total energy bar. All right, hopefully that clears it up, and I'll see you on the next video.